Hello, everyone, and welcome to the first Vita Science webinar of 2025, presented by the Teacher Enrichment Program of the Center for Excellence in Education. My name is Shannon Tyler, and I am the new Teacher Enrichment Program Manager. I will be hosting today's webinar titled AI and the Environment. We have an exciting speaker here to talk to us today, so without further ado, let's go ahead and get started. To begin, I would like to give some brief background information on our organization. The Center for Excellence in Education was founded in 1983 by Joanne DeGennaro and Admiral Rick Over, father of the nuclear navy and civilian uses of nuclear power. Its mission is to nurture high school and university scholars to careers of excellence and leadership in STEM. The Research Science Institute, or RSI, is a highly competitive 6-week summer science and engineering program open to rising high school seniors, and juniors are eligible to apply. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus work in science and technology research. Next, we have the USA Bio-Olympiad, or USABO, which is the premier biology competition for high school students in the United States. It provides the motivation, curricular resources, and skills training to take them beyond their classroom experience to the level of international competitiveness. Since CEE began administering the USABO in 2003, every member of the USA Bio-Olympiad team has medaled at the International Biology Olympiad. Next, we have the Teacher Enrichment Program, or TEP, which is the program that brings this webinar to you all today. It provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for you and your students. Last but certainly not least, we have the newest initiative here at CEE, which is STEM Lyceum. STEM Lyceums is a virtual club for high school students to engage in discussions and exploration of STEM and to learn about STEM career pathways from leading field experts. I am joined today by Rebecca Carter, who is the new program manager for STEM Lyceums, and she is going to be doing the back end of our Zoom webinar today, so thank you to her for doing that. To learn more about our programs and opportunities, please visit our website at ce.org. I am happy to introduce today's speaker, Dr. David Rolnick. Dr. Rolnick, RSI 2007 alum, is an assistant professor in Canada CIFAR AI chair in the School of Computer Science at McGill University and at Mila, Quebec AI Institute. Dr. Rolnick received his PhD in applied mathematics from MIT, and his lab focuses on innovations in machine learning driven by problems in climate change, including areas such as biodiversity monitoring, land use classification, climate model emulation, and materials discovery. He has served as the co-founder and chair of Climate Change AI, the scientific coordinator of sustainability in the digital age, and the Canada lead for the NSF-NSERC Global Center on AI and Biodiversity. Previously, he was an NSF Mathematical Sciences Postdoctoral Research Fellow at UPenn and an NSF Graduate Research Fellow at MIT. In 2021, he was named to the MIT Technology Review 35 Innovators Under 35 list for work in building the field of machine learning and climate change. Recently, he was named a 2024 AI 2050 Early Career Fellow. So, as you all can tell, he has quite the background, quite the resume. Thank you, Dr. Rolnick, for joining us today, and we're excited to hear your presentation.
Thank you. It's a pleasure to be here. I'm looking forward to the discussion. Please do drop questions into the Q&A. Let's get started. I work on AI and climate change. I don't think that the problem of climate change needs very much introduction. We're increasingly seeing its effects. They're becoming both more frequent and more severe. Everything from droughts to flooding to intense storms to heat waves. Depending on where in the world you are, you may have encountered one or more of these. Often climate change works by having more extreme weather of several different kinds. So weirdly enough, you can have flooding as well as fires, which is what some of Southern California is experiencing right now. We are very far from tackling climate change. This is a somewhat dispiriting graph where you can see the gap between the curve that we want to be at if we are to avert the most catastrophic impacts of climate change. This is the level of greenhouse gas emissions carbon dioxide, methane, and other gases emitted by society. This is where we need to be at, decreasing emissions to zero, and indeed to taking greenhouse gas emissions out of the atmosphere very, very fast if we are to avert really catastrophic consequences as determined by the UN's Intergovernmental Panel on Climate Change. Current policies are here. We are very far away from the green curve. If every country in the world were to meet its obligations under the Paris Climate Agreement, the agreement which the US is now no longer a part of, we would be here. So even if every country in the world were to keep those pledges, which countries, including the US, are very far from doing in general, we would be very far away from our goals. So there's a lot of work. And really, this calls for action in many different ways. I'm a computer scientist, and I am working to use the tools that I have at my disposal to help tackle climate change as one of the biggest crises that humanity really has ever faced. That is not the most powerful set of tools. I'm not here to tell you that AI is going to solve climate change. Unfortunately, we really need all people using the tools at their disposal to help tackle this crisis. So I'm going to be talking about the intersection of my own area of work, which is AI and machine learning, with climate action. But first, I want to talk about what really is AI, because it's a term that gets thrown around a lot. What is AI? It has a very general definition. Any computer algorithm that makes predictions, recommendations, or decisions on the basis of a defined set of objectives. That includes a particularly popular area now, machine learning. Most people, when they say AI now, mean machine learning. I'm mostly going to be talking about machine learning here. And machine learning algorithms are those that infer patterns from data instead of being told explicitly what to do. So if you give a computer the task of going through every possible move in chess and working out what's the best one, that's not machine learning. That's a symbolic AI approach. And machine learning has become extremely powerful recently, thanks to, in particular, deep learning and neural networks, which is one of many different machine learning techniques, including also random forests and Bayesian methods. And these methods, instead of being told directly what to do and going through all the possibilities, are given a large amount of data and pick out patterns that make it possible to predict what will happen in data that they haven't seen yet. Now, machine learning has some strengths. It's very good at performing straightforward tasks quickly and automatically. If a human can do a task, but it's kind of boring, like a data processing task, that is often a good match for machine learning. Machine learning is also good at finding subtle patterns in big data sets, because that's kind of how it works. That's its whole thing. Weaknesses include it's all about the data. So if the data is bad or if it's biased, then that can lead to huge problems. It also can't think outside the box. As an example of these two problems in one, there's a somewhat famous example where machine learning algorithms were designed to play video games with the standard settings on the video game and performed very well. But if you change the background color of the video game, they completely broke and failed to score well at all. That's something that a human would clearly be able to adapt to very easily. But because the machine learning algorithms are very sensitive to the data, even meaningless parts of the data that don't actually make sense in a sort of human way, they're not able to generalize in this way. So this is an example of how these kinds of problems can lead to huge issues. And generally, machine learning algorithms also can't explain reasoning. Normally, it's a situation where this is the answer, is what the algorithm tells you, and either it's right or either it's wrong, but you don't know why. You don't know, you don't get any logic because it's not doing logic. So having seen what AI is, having seen what climate change is, let's look at the intersection. If you're interested in a really comprehensive taxonomy of all the different ways that machine learning and AI are helping tackle climate change, we wrote a big paper. It's like 100 pages long. You can go through any particular area that you want, from climate modeling to heavy industry to buildings and cities to agriculture, forestry, and other land use, and look at all these different ways that machine learning is being used to help tackle climate change. I'm not going to go through all of these. I will go through some overall themes that we see, and then look through some examples in my own group's work. And if you're saying now there are ways that AI is making climate change worse, yes, absolutely. I'll also talk about that. Though I'm not going to focus on that as much because that's not the focus of my work. The themes that I want to talk about, first of all, improving operational efficiency. There are a lot of complicated automated systems which can run more efficiently using integrating AI and machine learning into controllers, like, for example, for controlling heating and cooling systems in buildings, in manufacture of things like steel and cement. Steel and cement, by the way, contribute about 15% of global greenhouse gas emissions, just making steel and cement, because we use a lot of them. So any small increase in efficiency is really valuable there. Gathering information, taking, for example, satellite imagery and estimating things like the amount of carbon stored in a forest, or where's deforestation happening in real time, or where's flooding happening, or what kinds of crops are planted there. That's the kind of data that can't be gathered at scale by humans, but machine learning can automate these systems to help inform policies and other kinds of interventions. Forecasting, so taking time series data and predicting what's going to happen next. Some particularly valuable applications here are in predicting the supply or demand for electricity, because in order to balance the electrical grid and better integrate renewables, we need to understand how much electricity is available at any point in time. If it's solar or wind, then the sun and the wind affect the amount of electricity available, and predicting demand, because that varies from moment to moment as well, and you need to make sure that there's enough supply to meet demand. Speeding up simulations is also a key area across different sectors. There are very good physical simulations of the Earth's climate and weather, for example, but they can be very slow, and machine learning and AI can help speed them up. And then accelerating the process of scientific discovery itself. Machine learning and AI are not a replacement for physical experiments, but they can reduce the number of experiments that you have to run in certain kinds of design contexts. So, for example, if you were designing materials for use in batteries or in solar cells, like perovskites, you might have to try a very large number of possibilities, and machine learning and AI can help reduce the number of possibilities by running simulations or by suggesting good candidates. I'll get to some of these specific areas in a bit more detail, but I want to touch on some key considerations first. First of all, AI is not a silver bullet. Again, it's not magically going to solve climate change. It's not even going to solve magically any one of these areas of application. It's only relevant sometimes, and in each of these cases, it's only relevant in conjunction with established tools from other fields and sectors. That really calls out the need for interdisciplinary collaboration. First, in scoping the right problems. I can't tell you how many times somebody from tech comes in and says, I'm going to solve this problem using AI, and they're solving a problem that's completely useless, or maybe it was already solved using existing methodologies. Incorporating relevant domain information. Again, tech is very good at coming in and not paying attention to the information and knowledge that already exists in a field and trying to reinvent the wheel. That is a huge problem, especially in the case of AI, because I'll get to this more in a moment, but there's definitely a culture in AI of we're going to learn everything from data instead of actually incorporating user needs. And then shaping pathways to impact, because when I give talks to like researchers in AI, they're often thinking about where they're going to get their next paper, but that does not actually translate into impact necessarily. Okay, so also worth bearing in mind, high impact applications are not always flashy. Like you see AI in the news, and that might be like self-driving cars. Now it's probably ChatGPT, but it used to be self-driving cars. Self-driving cars, like ChatGPT, are probably making climate change worse. We'll get more into that in a bit. But even in the space of transportation, like self-driving cars are going to make climate change worse. Again, I'll get more into that later. But if you're interested in using AI in transportation, you could be using it for predictive maintenance of railways. That's something that Deutsche Bahn in Germany is doing extensively, and it's leading to better railways. And that is also, aligned with climate action. So that doesn't necessarily make the news. The flashy applications of AI are not necessarily the ones that you should be thinking about here. And then the methods used are also generally not the flashy ones. That can either be because the methods are really simple. Like in some cases, all you actually need is linear regression or random forest, or one of these very simple machine learning approaches. Sometimes you actually do need a cutting edge machine learning or AI approach, but that's often not the ones that are going to make the news, or if you're an AI person, the ones that get talked about a lot. These are generally innovations that are driven by particular applications and informed by user needs. And the culture, again, in AI is very much, I'm going to design an algorithm that solves everything, solves every problem, for example, in labeling images. And that actually doesn't work. By trying to solve every problem, you often end up solving none of them very well. Now, those innovations in AI are useful. You can build on them and design things that are specifically relevant to particular applications, but by themselves, that kind of blue sky innovation isn't enough. And I'll get into that more in the next slides, because that's what my lab works on. Like, we're computer scientists, so we work on innovations in AI, but we're working on innovations in AI that are scoped to meet the needs of particular users. And then I should note, since so many people, when they say AI now, mean ChatGPT or maybe DeepSeek now, or another large language model. Large language models and other generative AI are generally not useful here. And by not useful, I don't mean they're overkill. I mean, they're actually counterproductive. Like if you asked ChatGPT to forecast electricity on the electrical grid, it would give you the wrong answer. And a specialized AI algorithm that's designed to do that is going to give you the right answer. And that was the case with all of the applications that I gave you. all of those are not actually using these kinds of large-scale generative AI, large language models, large vision models, large generative vision models. Those are not the tools that are being used, and they don't work in these contexts. So yeah, worth bearing all these things in mind. Okay, let's take a look at some examples. I'll talk about as many as I have time for. I don't know how many I'll have time for. First, I want to touch on something that falls under operational efficiency. So here, we're going to talk about operating power grids. There is a problem that you have to solve, this math problem. If you are going to operate a power grid, and you have to, what you're doing here is you're basically determining how much power needs to be produced at every generator on the grid. Now, that generator could be like fossil fuel based, it could be wind, it could be solar, whatever. And if it's wind or solar, you don't actually get to control how much power is being produced. But for some of the others, you do get to control. In order to solve this problem, you have to do a lot of math. And it's a non-convex optimization problem. So if the computer science experts in the room, you know that means it's really hard to solve. It takes a long time. And so since exact solutions take too long, in practice, what grid operators do is they simplify the problem and they don't get the right solution. And they end up wasting power. And this is particularly a problem with solar and wind for reasons I won't get into. So you end up producing more power than you need, which is just bad. It's bad from a climate perspective. It's bad from every perspective. Now, naive AI algorithms can approximately solve this problem. But there's a big caveat, which is it's a constrained problem, which means you're trying to minimize this thing, which is basically minimize the power, subject to the constraints that it satisfies demand and that you aren't actually, breaking your generators. So AI can approximately solve this problem, but it approximates everything if you're using a standard deep learning algorithm. A standard deep learning algorithm sort of you would add a penalty for violating these constraints, like a soft penalty in the loss function. Don't worry if you don't know what that means. That's just for the people who really like the details of the machine learning. If you do that, though, you end up approximately solving the problem, but also approximately solving the constraints. And that breaks the constraints. And so you actually violate the conditions of power flow on the electrical grid. You have a blackout and people die. And so nobody would ever use an AI algorithm to solve this problem if people might die. So what we've done is we've designed machine learning algorithms that can actually optimize this while enforcing the constraints. So you don't break the physics and you also do get a good solution. And it's also much faster than traditional math. So the next example I want to give is in gathering information. And here I want to talk about biodiversity. So here you can see a map of the world colored by how many species are at risk of going extinct from climate change. And there's just a vast amount of risk in the global south, from South America through Australia. Here's a map of where we have biodiversity data. It's kind of the opposite. It's all in the global north, particularly in North America. This is a plot of data on birds, by the way, which is which are the best studied species by and large. But lest you think that this is a problem for the global south only and not a problem for America, that is totally wrong too. Let's zoom in here. This is Massachusetts. All the data on birds is actually around Boston and maybe a few other big cities. But if you look at even any rural area of the US, we don't have data on that either. So if you're going to try to make decisions about how to preserve biodiversity or all of the things that biodiversity interacts with, like forests and agriculture, you need to have much better data. And you need to have data at a scale which has been previously unattainable. So I want to talk about two projects that we are working on to try to build up that data at a scale that hadn't been possible to gather before. So first is to infer habitats with remote sensing. And this is leveraging the fact that you can actually get a lot of information about where species might be based upon what you can see from satellite or aerial imagery. So for example, here, there's this particular kind of bird. It's found in meadows of a certain age, like hay meadows. And oftentimes what people do if they're trying to conserve this rare bird is they just delay the time at which they hay. I'm from Vermont, and it's not actually a big deal. You just change the timing of the haying, and then you got your hay, and you've also saved your bird. But you need to know where the bird is. And so this is an opportunity where you can actually not just rely upon observations, you can actually say from satellite imagery, maybe this is a hayfield of the right age. Maybe this is a good place for it. This is the kind of thing we've done in this paper, where we're able to develop basically checklists of species that might be present in a given location based on the habitat that we can infer. And then we've also found that if you add in the species that have been observed there, sometimes you've got birds, but you haven't got butterflies, for example, because birds are much more observed than butterflies. If you want to predict butterflies, you can actually predict them better if you add the birds in, not surprisingly, because species form ecosystems, and when you know something about one species, you know more about the other species. So this is one of the ways in which we're working on this. There's another way that I want to talk about. Oh, and this is the kind of map you can get, by the way. This is a California quail. This is a map of where we think the California quail is going to be at like a habitat level. It's found everywhere here, but it's not found anywhere, right? Like you're not going to find it. You're not going to find a California quail in the wrong habitat. So this is a map that can like make it much more precise. Now I want to talk about our second project in biodiversity monitoring, which is using physical devices to gather data at scale on insects. Insects represent about half of all global biodiversity, and they're critical to every terrestrial ecosystem, critical to agriculture, critical to forests. And when insect biodiversity goes down, fun fact, pest species go up. So actually, even if you're thinking like, oh, insects include pest species, that's bad for agriculture. No, more biodiversity of insects is actually great for agriculture because then you get more pollination and you also have reduced pests. So if you're trying to understand insect biodiversity, you either need experts, and there are very few experts on insects, despite the fact that they are half of all species, or you can use new automated monitoring systems, which don't remove experts from the loop. They just give the experts the ability to cover a lot more ground. And so these are hardware systems which are solar powered, and they attract insects with a light, and they photograph them, and then you can identify these species. So this is together with an international team, the Automated Monitoring of Insects Coalition, and we have AI algorithms that can process the data coming off of these automated systems. So you can just leave it out in the field for months at a time, then plug it in and download all this data, process it automatically. And you can flag particular species of interest, like an invasive species. And so what we're doing is we're detecting insects. In this case, we're focusing on moths. And we're first classifying things as moths or not moths, and then we're going to individual species. And it looks like this. You can get all this data processed automatically. Here is us setting it up in the rainforest in Panama at the Smithsonian Institute research station there. And one of the challenges we actually have been encountering, which I won't have time to talk about, is that when you set these things up in extremely biodiverse areas, you often end up with actually a lot of new species because about 80% of all insects have never been discovered before. So this is a problem for AI algorithms. It's kind of also an opportunity. And so we're developing algorithms now that can help you pinpoint what might be a new species. Because when we set this up, we actually found 300 new species at this one location. Okay, so we also do a bunch of other things. Here's forecasting crop yield. I'm not going to talk about it in depth because I want to make sure I leave time for questions and discussion. But here we're trying to predict crop yield. We have very limited data, and so we're trying to generalize across lots of different places. We have algorithms that can generalize across many different places, many different crops, provide information to governments, from the US government to the government of Togo, on where crops are and what we expect the yield to be. These algorithms end up actually being useful in some other contexts too. So this is something we see again and again. We design an algorithm for one application, then it ends up being useful in other applications because they have some similar challenges. We speed up simulations of climate and weather. If you're trying to, for example, suppose you are the government of Phoenix, Arizona. You have a map of temperature that looks like this. That is not very granular. You've got like one box for all of Arizona. And in fact, it turns out that Phoenix is a microclimate. So Phoenix has very different temperatures than the area around it. So if you're going to model climate and weather, you need to have a much more precise notion of what's going on right there. So we use AI to do two things. First of all, we use AI to approximate radiative transfer, which is a particularly time-intensive part of climate simulations. This is why you end up with these very grainy maps. It's because you don't have the computational power or time to get a really fine map. We understand the physics great. It's just we don't have the computational power, even on supercomputers. We incorporate some physics into these algorithms, and we're working with the government of Canada to integrate that into Canada's global climate model. The other thing we can do is we can do the thing in movies where, you know, somebody says, enhance that image. We can actually do that using AI. It's a pretty standard thing with AI now. It's not as good as in movies, but it is still pretty good. But these algorithms were mostly not designed to do this with like clouds. Clouds look very different from faces. So making a blurry face sharp is something algorithms can do well, but doing it with climate and weather data has been very hard. So we've integrated different kinds of physics into that, like conservation of energy. And we've also used these cool tools called Fourier neural operators that mean you can actually predict it much higher resolution than you've seen before. And then the final thing I want to touch on is we've worked on materials discovery. So there are all these settings where we need what's called electrocatalysts. So materials that can catalyze reactions to, for example, produce green hydrogen, electrofuels, to store electricity in these kinds of fuel sources that you might use in lots of different contexts. Also to produce efficiently things like ammonia and other compounds from electricity, where there is use of fossil fuels going on right now. So finding these catalysts, we have catalysts, but they are not necessarily as good as they can be. And that's a huge potential for the energy transition. Finding these new catalysts currently requires slow quantum chemistry simulations, and there are also a lot of possibilities to choose from. So we're using AI to help with both of these problems. First, we're quickly evaluating candidate catalysts, so you don't have to do the slow chemistry simulations. And second, we are suggesting promising candidates. So this is not a replacement for experimentation, but it means you have to do fewer experiments. You can quickly evaluate some things in simulation, and we can suggest candidates that you might want to try in the lab. Okay, so I want to close by mentioning AI can also negatively impact the climate, very significantly. In fact, arguably, AI is probably making climate change more worse than it's making it better. Sorry, that was bad English, but you know what I mean. The different ways that that's happening. The thing that everybody thinks about is energy consumption, and that's getting to be an increasingly big deal with things like ChatGPT. Energy from computation is very big for some AI algorithms, not at all for others. There's also embodied emissions from a hardware, which is like when you're making a server, what was the energy and the fossil fuels used in making that? And there are also issues to do with water consumption, heavy metals, and other sustainability implications. Again, this is very low for some algorithms and very high for others. ChatGPT, for example, is extremely high energy. The algorithms I was talking about just now, those are actually really low energy. Some of the algorithms that we use, which are being now deployed by governments around the world, might use literally a billionth as much computational power as ChatGPT, a billionth. So there's huge variation, right? And so it's worth bearing this in mind as we've seen a growth in these enormous AI algorithms. And I would argue that one of the things to think about there is not can we make them more efficient, but how much do we actually need to use them? We probably want to use ChatGPT or other large language models in certain contexts, but probably not in nearly as many contexts as it's being hyped for right now. Like generative AI is basically half of all US venture capital funding right now, which is ludicrous given that human society is about more than generative AI. And again, none of the applications I talked about here require ChatGPT or anything like that. There are also application-related impacts. AI is used extensively in fossil fuel exploration and extraction. It's leading to as much as a 5% production boost in some cases, and as much as $500 billion in additional profit for the industry. Already. AI-enabled advertising systems are also used ubiquitously. All of online advertising depends on AI. And that is designed, in some cases, to increase consumption. Online advertising does many things, and it can be beneficial in certain contexts, probably, but it's definitely contributing to things like fast fashion, which is the fashion industry is the third biggest contributor to climate change after agriculture and construction. So there are huge ways that AI is facilitating climate change. Autonomous vehicles. I talked about self-driving cars. They're probably making climate change worse. Why? Each mile driven gets a little bit more efficient, right? The car is better at driving than you. The car may or may not be better at driving than you, but it is likely that self-driving personal cars are going to decrease the barrier to driving. People will drive more. Now, there can be benefits, right? A really good self-driving car, if it exists, could be good for public safety, potentially. But from a climate perspective, it's probably worse. Now, the same technology, however, could be used, for example, in self-driving buses or in integrating different kinds of freight transport. So there are a lot of ways you can use potentially the same technology in ways that are more or less beneficial from a climate perspective. And so this is what I really want to leave you with. Overall, when you hear about things like AI for good or AI for climate, you shouldn't just be thinking about new good applications of AI. You should be thinking about shaping all the applications of AI to be better for society, steering everything that one does and thinking about this as one lens. Of course, it's not going to be the only lens. There will be other lenses, like, again, health, public safety, and presumably profit as well. But having all of these be consciously thought about is really going to be key for society in moving forward. I want to thank, well, actually, no, I don't want to, I will thank you, and I will thank all the people who contributed to this work, but I first want to give you more resources. Forgot I had the slide here. This is the nonprofit that I co-lead called Climate Change AI. We have a lot of different resources for people getting started in the space, or experts as well. We have reports aimed at everything from researchers to policymakers. We have events. Upcoming event is at iClear 2025. It's physically in Singapore, but it is also virtually available for free online. You can look at about 1,000 past papers from all of our conferences and other events online. We have summer school every year. It's not just for students, it's also for people from other different areas. That is for working professionals and teachers as well. We have funding programs like our innovation grants program, and we have a newsletter. If you sign up for one thing, I would recommend signing up for a newsletter because it summarizes all of these other things every month. And you can hear about what's going on in the space of AI and climate change. We also have a community platform where you can ask questions and get in touch with people around the world. Thank you so much for listening, and thank you to my wonderful group at McGill and Mila for all of their work on all of these different research projects, and also to our collaborators. Thank you so much. I look forward to the discussion.
I have a question regarding your simulations. I know you said that some of the previous simulations can take up to months, even on a supercomputer, and you guys are working to kind of speed that up. So typically, I know I'm sure it depends on the project, but typically, how long do your simulations take, or what is the difference between the time of what used to be and what you guys are doing now?
Look, so I don't want to do a straight comparison because we're approximating a particular piece. Like if we run something in minutes, that's not that it's minutes versus month. It's minutes versus that particular piece. I haven't got a time comparison exactly, but we should be thinking about like orders of magnitude, but not that many orders of magnitude.
I know you said you didn't have much time to talk about it, but can you elaborate a little bit on the how you guys overcame some of the challenges that you guys did come across in the projects? For example, you were talking about the rainforest, seeing the new species in there. What did you guys do to overcome that?
So there is a literature associated in the AI world associated with what's called open set recognition. And so we're building open set recognition algorithms that can not just say which out of all the species that you know is the best match, but is it actually something that isn't in the set of species that you know? Because typically an AI algorithm is designed to sort of give the best match from what it knows. It's very similar to, you can't blame the algorithm. Like, clearly, that is a very reasonable thing to try to do, and that is how these algorithms are designed, generally speaking. But the best match is often not the correct match if there are a lot of new species. So, open set recognition algorithms. I'm not going to go into technical detail here, but we'll have a paper coming out in just a few days, actually, on this.
Nice. Thank you. We did have a question come into the chat, and it is, are there any tools/simulations available that teachers can use in the classroom to have students experience working with AI on climate
So
problems?
it's a great question. I actually think so, and I can think about it, but the reason why I hesitate a little bit is I'm not sure that like grade school students should be learning yet about AI on climate problems because again, AI is not the most valuable set of tools that people should be learning in order to help tackle climate change. Don't get me wrong, it's powerful. And if people are working on AI, they should absolutely be thinking about these things. But in today's world, there are so many ways in which people are taught, oh, AI is going to solve everything. Let's do AI and blah, blah, blah. And I think that, it's more important to be working on climate problems just period and using human tools, especially since in elementary or high school, students don't know any real AI, right? So I think that it's more important to get them asking the right questions and engaging with the problems. And then some of them will end up learning tools related to AI, and some of them will end up learning tools related to other things like writing or law or art that they can engage with these problems, they can use to engage with these problems. And so I think framing the problems and framing like who needs to be designed for is more important, and they're not ready probably if they don't have already advanced AI skills, which they're ready to like deploy in particular ways. So that would be my thought. You can find like little toys online. Certainly, if you're teaching AI, you can definitely be teaching about some of these applications. And you should also be using there are a bunch of tools that track how much energy a particular AI algorithm is using. So if students are coding AI algorithms, they should definitely be tracking the energy usage as well to just get them thinking about the fact that these things do use energy. If you're a student using an AI algorithm, it's going to use very little energy. But big AI algorithms absolutely do that. Anyway, so these are some of the things to think about. It's a good question.
Yes, thank
I
you.
need
That
to
was a
take
good question.
undergraduate interns normally in my lab because I think that generally speaking, this is something that comes later if one's already like a graduate student or a further researcher or practitioner in AI. The connections between AI and wildfires and the Santa Ana winds, great and timely question. There are different ways that people are using AI in wildfire science. You can use AI to predict like I think the parts of this that I think are most promising and are like in some cases actually being used at scale. So you can use AI to track different aspects of land. And one of those is like fuel moisture content. So it's like how much wildfire fuel, how dry is it? That's something you can track using satellite or aerial imagery. And we actually have some work on that. There are a lot of different approaches you can use to do that. And then the other side of this is if you are trying to find failures on power lines, what's called predictive maintenance, and that can often lead in certain places to, such as in Southern California, to wildfires when like power lines arc or spark or etc. So those two things, using satellite imagery to find fuel moisture, to identify fuel moisture content, and having cameras that can like watch power lines for issues. Those are super promising. They're not widely used, I think, in fire prevention yet, but they are used, as far as I understand it. Now, the other things that people are looking at are like modeling how you should understand how a fire might spread and then how you might intervene there. Those seem potentially a little bit more speculative to me, but people are working on that research. So those are some ways. I don't think there's anything specifically to do with the Santa Ana winds. I mean, that's a regional thing. People definitely work on weather modeling extensively. There are many either public or private entities that are doing weather modeling using AI. And so that is that's like widely used across the industry. Many of the best weather models now involve AI.
Can you talk just a little bit more about the negative impacts that you were talking about? So kind of, how do we overcome those? What do you see the future for these things? Like, where do we go from here as, again, like we said, AI is getting nothing but more popular?
Well, it's what I'd like to happen, and is what I think is going to happen.
Mhm.
What I think is going to happen is that people will continue to build more and more large AI systems, and there's an arms race going on now in AI. And I don't even really know why in many cases. Like there are definitely AI uses for some of these very big AI algorithms, but I don't think there's quite so much use for these things as people think there is. It doesn't really seem to me to be worth, $500 billion of US investment, private investment, but it isn't worth every country saying we need our national version of ChatGPT when it's not clear to me what ChatGPT is actually doing for the US economy or society. I would like to see a reduction in massive AI algorithms, and I think eventually a bubble will burst, but it may take a while, and there may be a lot of people who are out of a job because people think that their jobs should be replaced by AI systems, or because we're just throwing all that investment in AI instead of other stuff. I am seeing a lot more applications of AI in all the areas that I mentioned. That stuff is being deployed. Like this is not speculative. This is being used by lots of companies, by lots of public entities. People are using AI productively in these different ways. It's just being done in addition to all of these other things. And it's swamped by the large language models, right? So I would love to see maybe some more of the stuff I was talking about and some less of the let's build big AI systems for I don't know exactly what purpose.
We did have one more question come in. It says, maybe not related to climate change, but what is your take about AI, ChatGPT, and DeepSeek and the veracity of the research they represent?
They aren't search algorithms at all. They don't do search. They are generative algorithms. A generative algorithm is designed to produce something that sounds right. It's not designed to produce something that is right. So when you ask a question to ChatGPT, it's not just that it might be wrong. There is no reason to suppose that it's right. It's like if you're dreaming something and you suppose somebody asks you a question in a dream. This is how I often think about it. If somebody asks you, like, what's the capital of France? You're going to give the right answer in a dream because you know that. But if somebody asks you, like, what is the smallest city in France? Or if somebody asks you to do a complicated like logic puzzle, you're not going to be able to do that in a dream. You'll make something up. Your dream mind will come up with something that sounds plausible. And that's basically what happens with ChatGPT. It's a lot more sophisticated. And so it's able to memorize a lot more things. So there are a lot more questions where it can come up with something that's very sensible than just, what is the capital of France, right? And that keeps on getting more and more. And it's been trained with basically the entire internet. So it is able to produce like correct answers a remarkably large amount of the time. But that's almost an accident because from a mathematical perspective, what it's designed to do is maximize the probability of being close to a correct answer. And being close to a correct answer means that it's actually basically just trying to sound right, which is why it's so good at like, if you ask it, take this report and make it into a poem. Great at that because it's all about sounding right. And so if it's trying to make something sound good, it can make it rhyme or scan. It's not going to make a good poem, like one that actually has meaning behind it, but it can make it something that's stylistically something that you want. And so it's really all about style, and the content is almost an afterthought. Now, there are many ways in which that's useful, right? That could be useful, for example, people are using ChatGPT in order to do simple tasks where one does want something to sound good. That's totally reasonable. But if you're trying to replace search, that's terrifying to me. Because it's much more energy intensive than search. It uses orders of magnitude more, 10 to 100 times more energy probably than Google search. And Google now is using generative AI automatically in its search. You can see that generative AI at the top, and you can't even opt out. And it's also not reliable. Again, it's not a search algorithm. There's no reason why it should be correct. Now, there are ways to do like this thing called retrieval augmented generation, RAG, where you are sort of mixing search and generative AI approaches, but still it's basically unreliable.
Thank you so much for taking the time to be here with us today. We really appreciate it. Last but not least, before we sign off, I would like to give a special thank you to our sponsors for supporting us and making these cost-free webinars possible for you all. I'd also like to thank all of you all in the audience today for attending this webinar. We hope you enjoyed it. We hope to see you at our future events. You can check them out on our website.